Okay, so we've talked about velocity, or sorry, displacement versus time, giving us velocity. So there's displacement, there's time, and so our graph that tells how a thing moves over time would tell our velocity. So we've got a low velocity here, a higher velocity here, a higher velocity right here. Now what we're going to do is we're going to take velocity and plot that versus time. So velocity is how displacement changes over time. All right. So if we take velocity versus time, what's that going to tell us? What kind of graph is that going to give us? Well, that's going to give us a graph that talks about acceleration. And that's really what a velocity versus time graph is. All right. So we're actually going to be dealing only with average acceleration, honestly, or that is constant acceleration. For example, if you're moving 5 meters per second and then you move 5 meters per second a couple of seconds later and then 5 meters per second a couple of seconds later, you've got a constant acceleration, right? Well, that 5 meters per second is also your average acceleration right there. So what I'm going to tell you is, it's kind of redundant in just a second right here regarding the secant line and also the tangent line as well. If something has a constant acceleration, which we are only going to deal with, what this means is that the instantaneous, that is the tangent, here's a tangent right here, all right? The tangent of that line, and the average, so this is the secant line, are going to be the same thing. Let me show you a picture just to kind of illustrate this. Right? This green line, this right there, this green graph, is the line created by a velocity versus time graph. So we've got time on the x-axis and velocity on the y-axis right here. And velocity over time is acceleration. But look, we have this acceleration, this green line curving. We are never going to see that in our physics class. We're never going to see a changing acceleration where it's a greater slope here, so it's greater acceleration, and then less, and then less. Well, we might see it changing kind of in straight lines like this, though. This is what we mean when we say a secant line. That is a line that connects two parts of an otherwise curving graph. So while you have a greater acceleration here, so greater acceleration, and up here you have a little bit less acceleration right here. What the secant line does is that gives you the average. Well, again, we're only going to be dealing with constant accelerations. The other thing is this, and I've been drawing this whole time, these arrows sticking off right here and right here and right here. Those are tangent lines. That tells you the instantaneous acceleration at any one point. All right, so like this instantaneous acceleration right there would be negative, and that instantaneous acceleration there, right there would be just about zero. So just so you know that the tangent line is the instantaneous acceleration, just like the tangent line of a position versus time graph is the instantaneous velocity. Instantaneous acceleration on acceleration graph is the tangent line. The average acceleration, this is acceleration 1 plus acceleration 2 divided by 2, this A average right here. That's the secant line. And again, like I said, it's kind of redundant because we're only going to deal with average or constant accelerations. So let's take a look at this for example. Here are 4 different graphs. We've got graph A, B, C, and D. Okay? So we want to look at 2 things to say if the object is decelerating or accelerating. We want to see what the initial velocity is, V initial, and we want to look at the slope. Is it sloping up or is it sloping down? Does it have a positive slope or a negative slope? All right, so I'm going to do all these in 4 colors. This first one here, actually, you know what? I'm going to take this and I'm going to delete these guys. I'm going to delete all that, actually. All right, I'm going to start over with just red for A. All right, so right here, what's our initial velocity? Well, we have some positive initial velocity right there, right? So velocity, come on now, there we go. Velocity is positive, and look at this, we have a positive velocity change over time. That should be a V, shouldn't it? Positive V, or delta V, over time. So we have positive acceleration. So it's going to speed up. It's going to speed up in the positive direction. Let's take a look at the second one right here. I'll do this one in, I don't know, dark green. All right, B. All right, we have a positive, the velocity is positive, but the acceleration is negative. We've got a downward slope right there. So negative acceleration, if I can go back, the first one speeds up positively, in the positive direction, I should say. Here we have something moving positively, but it starts to decelerate, so it slows down in the positive direction. Okay, so it's actually it's slowing, and getting closer to zero or closer to no velocity at all. All right, so let's go to this third one right here. Let's do this one in blue. All right, C. At C, we have a negative initial velocity, right? So it's got a velocity in the negative direction, but it has a positive velocity change over time, or it's got a positive acceleration right here. So that means that it's going to slow down, all right? Slow down in the negative direction. That means right here it's going backwards, but it's coming to us, over time it's coming to a stop because it's approaching zero velocity. It's like you're backing up, but you're slowing down, and now you're stopping right there. So it slows down in the negative direction. And finally, this last one, let's do this one in pinkish or something, I don't know. We have a negative, velocity is negative, but we also have a negative acceleration, right? Or you might say a negative velocity and I'll just call it a negative acceleration. So therefore, it speeds up in the negative direction. You're going backwards right here, and you're going faster and faster backwards because your velocity is increasing just in the negative direction. That's what we mean when we say that. Okay, so when we have a position versus time graph, we'll do this right here. Okay, position versus time, just to review. The slope equals the velocity, okay? Because position over time, x over t, is velocity right here, all right? This is interesting. On a velocity versus time graph, the slope equals the acceleration, so that makes sense. So let me sketch that real quick here. So velocity versus time graph, the slope equals the acceleration, all right? And the area under the curve, what we mean by that is for a certain amount of time, between here and here, we'll say, this area between time one and or time initial and time final equals the displacement. In the next graph, I'll show you what I mean by that in just a second. So that area equals the displacement for that graph. We talked about this already. The slope equals acceleration. All right, we got that right there. And on an acceleration versus time graph, all right, so here's the acceleration versus time. The area under the curve equals the change in velocity. So if we have, let's say, a positive acceleration, like that, all right, so it's some value positive. And remember, we're only going to deal with constant accelerations. Then that means for a certain amount of time between, like, say, here and here, the area under the curve will give you the velocity. Just like in the previous one, the area under the curve gives you the displacement. I'll show you an example and tell you why. Okay, so this one right here, this is a velocity versus time graph. Okay, velocity over time. So v over t equals acceleration, right? A change in velocity over a change in time. All right, but what if, and let's just say, for example, let's ignore this part right here where it's got a certain velocity and then it speeds up, it's got an acceleration and another velocity. What if it just had a constant velocity? All right. Well, there's no change in velocity over time, so therefore with a flat line right here, there'd be no acceleration, even though you would have this 1.5 meters per second velocity right here. But what if you were to take velocity times time? That right there. So velocity times time. Oops, I'm kind of giving it away, sort of. Velocity times, sorry about that, time equals, what is it? Well, that's our displacement. Because we know that a displacement, change in displacement over time equals velocity. So that means if we bring a time up, multiply it times the velocity, that tells us the displacement. So we're really just taking this area right here, the height by the base. And so this is the displacement. It's also true if your velocity changes. All right, so you have an acceleration and your velocity is changing. That's okay. Between 0 and 5 seconds, just find the area of this as well, and that will also tell you, well, you have to add these two displacements together, but that and that together is going to tell you your whole displacement for that whole amount of time. So all that in right there. Sorry, that's so messy right there. But you can find the area of a box, and hopefully you should be able to find the area of a triangle as well, which is 1/2 base times height, right? So the area under the curve in a velocity versus time graph is displacement. All right, and so here are guiding equations for finding or for determining what kind of graph it's going to look like. All right, so position versus time. All right, change in position. In fact, let's just bring this x initial over there like that. So it'd be x minus x initial, or really just change in displacement would equal initial velocity times time plus 1/2 acceleration times time squared right here. Well, ask yourself, what is the relationship between our displacement and time? All right, because we're plotting displacement versus time right here. Well, we've got this square right here. As long as there's an acceleration, then that means that as long as acceleration isn't 0, then that's going to make this a curve. So if there's an acceleration on the position versus time graph, you're going to have a curve, something like that. All right? But look at this. What about for a velocity versus time graph? Velocity versus time. What's the relationship between velocity and time? All right, well, again, if we do the same thing as before, if we bring that over and we have v final minus v initial, that really just says the change in velocity is acceleration times time. All right, well, what's the relationship between the y value and the x value right here? Well, it's just linear if we have a constant acceleration. All right, so that should be a straight line, just like that. So these two equations, this was, I think, our first one that we derived, and this was, I believe, our fourth one that we derived, should look very familiar to you, and they are the guiding equations that we say helps us determine what kind of graph it's going to look like. So we're going to look at that a little bit later once we get into kinematic graphing, but these two are big, especially determining the shape of the graph. Hope that helps. I'll see you in the next video.